In the natural world, the elegance of collective behavior is on full display. Take bees, for example. They perform complex dances to signal the location of a nectar rich flower to the rest of the hive, or ants, leaving behind pheromone trails, indicating to the colony a path to a valuable food source. These small individual actions, guided by simple rules, seem almost inconsequential on their own. Yet, when combined, they give rise to a sophisticated, unified swarm intelligence capable of solving complex problems and adapting to ever changing environments. As it turns out, we can actually use this brilliant swarm like behavior to our advantage to help solve some of the most challenging optimization problems. In the mid 1990s, Dr. James Kennedy and Dr. Russell Eberhardt decided to try to harness these principles for optimization problems in computing. Edward Wilson writes in his book Sociobiology, The New Synthesis, when referencing a school of fish, in theory at least, individual members of the school can profit from the discoveries and previous experiences of other members of the school during the search for food. This suggests that social sharing of information offers an evolutionary advantage, which is the fundamental concept leading to the development of particle swarm optimization. By blending personal learning with social influence, Kennedy and Eberhardt created an algorithm that mirrors the adaptive intelligence of natural swarms, capable of finding optimal solutions in complex, multidimensional spaces. To illustrate the power of this approach, let's imagine we need to determine the optimal location for a new warehouse for a business. The goal is to minimize the distance to stores in order to minimize transportation costs, while also being far enough away from residential zones to avoid disruption. In this problem setup, each particle would represent a potential warehouse location, and a fitness score would be determined based on the distance to stores and proximity to residential areas. As the algorithm progresses, particles will communicate with each other and converge towards the best solution. First, let's understand how a fitness score is calculated. This contour plot shown here was computed based on a fitness function. This lighter area is where the fitness is the highest and is the optimal location we want our particles to find. We can instantly spot where this best fitness is, however, the particles are completely blind to this. They have to compute a fitness score for each step they take to help determine which direction they should go next. For now, let's just focus on one particle and how it computes a fitness score. Initially, the particle doesn't know its location, so first it calculates a fitness score based on its current position. Remember, we're aiming to maximize the distance from residential areas and minimize the distance to stores. The particle finds the closest residential area and records that distance. We choose the closest because it represents the worst case scenario for residential disruption. Meeting this requirement ensures we're far enough away from all other residential areas, so no need to track the others. We then find the furthest store and record its distance. We track the furthest store for the same reason, as it represents the worst case scenario for distance to stores. Now, it's important to note that the closest residential area and furthest store will change depending on where the particle is. But to compute a fitness score for this particular location, we take the distance to the closest residential area and subtract the distance to the furthest store. The idea here is that if we increase this distance to the closest residential area and decrease this distance to the furthest store, which minimizes the amount we are subtracting here, that will overall drive this fitness score to an increasing value. So here we are 25 miles away from the closest residential area and 100 miles away from the furthest store, so our fitness score is negative 75. Since that is our first calculated fitness score, it's considered our best score so far, so we save this location as this particle's best fitness, which we will indicate with a blue star. Now, since we have a swarm of particles, all other particles also have their own personal best positions too, and only one of them we will mark as the best fitness position of the entire swarm, which we will indicate with a yellow star. Now, back to our single particle, when it initially spawns in, we give it a random velocity just to get it going. Once it has moved, it calculates the fitness of its new position. Here, we get a worse fitness score than our personal best, so we don't update it. Now, to determine where we go next, this time we've got some information we can go on to help guide our particle in the right direction. First, we have the velocity vector we use to get to this location. This is basically just our inertia, since an object in motion stays in motion with the same speed and direction. Next, we know where the swarm's best position is, and we should probably head in that direction to investigate further. So let's draw a vector pointing to that location. This will be our social vector. Next, we also know where this particle's own personal best position is, and it's still definitely worth going back to that area and investigating more to see if the fitness improves any further. So we will draw a vector pointing to our personal best position too, and call it our memory vector. Finally, we perform vector addition by adding all three of these vectors tip to tail, and with this, we can draw our new velocity vector. Now, in the algorithm, you can apply weights to these vectors so that you can vary the impact each component has on particle movement. Maybe you want higher bias on social influence, so you would increase the weight for the social vector. Or maybe you prefer the particles to explore a little more, so you can vary its inertia or memory vector. So this is where our particle moves to next and the cycle repeats. This process continues iteratively for each particle in the swarm. As particles move, they update their personal best positions based on their discoveries, simultaneously being influenced by both their individual experiences and the swarm's collective knowledge. This delicate balance between independent exploration and social learning guides the entire swarm towards converging onto the optimal solution. It's a dance of individual initiative and group wisdom, mirroring the elegant problem-solving behaviors we observe in nature. Now, you might be asking, couldn't we have just solved this using an exhaustive search method where we try every position in our search area to find the optimal location? And to that, I would say you absolutely could, and in fact, I might even recommend it for this particular problem, because it's such a tiny search space that the time to solve is negligible and it ensures that you get the correct answer every time. And yes, it is possible that the particle swarm approach can give you an incorrect answer. This can be due to not having enough particles in the swarm or not giving the swarm enough time to adequately explore the search space. However, where the particle swarm algorithm has the advantage is higher dimensional problems. Let's say, for example, we needed to scale this problem. Instead of finding the optimal location for one warehouse, what if we needed to find it for 3 warehouses? This problem grows exponentially for a solution like exhaustive search, because the position of each warehouse can directly affect the fitness of the other warehouses. If we take our 100 by 100 search space, there are 10,000 possible locations. Then, since we're dealing with 3 warehouses, we have to evaluate every possible combination that 3 warehouses can be arranged in these 10,000 possible locations, which we can compute using the combination formula. So there are over 166 billion different combinations we'd have to compute a fitness for. And if we say it takes about 10 microseconds to compute a fitness score, we're looking at about 19 days to solve this using the exhaustive search approach. Meanwhile, using the particle swarm approach, we can get an answer in a few seconds. It may not be the perfect answer, but it's often worth the time that we save. If you're interested in diving into the code and exploring the implementation yourself, I've posted the Python scripts on my Patreon page linked below. Here, you can play with the variables like the number of warehouses, the weights of the vector components influencing particle movement, and set any number of stores in residential areas to make the problem more interesting. In my experience, nothing beats hands-on learning when it comes to understanding new concepts, which is why I've chosen Brilliant to sponsor today's video. Brilliant is incredibly effective at illustrating core concepts in math, data science, programming, and artificial intelligence. What sets Brilliant apart is their meticulously crafted curriculum. Instead of passive learning, they offer a fun, gamified experience that challenges you to apply concepts immediately, reinforcing your understanding. Complex ideas are broken down using intuitive graphics and animations, making abstract concepts tangible. As you advance, you gain XP to compete with others, keeping you motivated to continue learning. They've got several courses on computer algorithms like binary search and insertion sort. They've even got courses on neural networks and quantum computing. To try everything that Brilliant has to offer for free for a full 30 days, visit brilliant.org/B001 or click the link in the description. You'll also receive 20% off an annual premium subscription. I want to thank Brilliant for sponsoring today's video and thank you for watching.